Okay, thanks very much for that introduction. Very nice. So I'm going to talk today about the setting and structure and placement of Meguma low gold deposits, and then Dan's going to follow up with, discussion about everything else other than those topics on Meguma gold deposits, I would assume. Anyway, as he sort of indicated, the work that I did when I was with DNR is going to be what I'm going to be discussing in this talk. In some ways, I thought, well, this has been like 7 or 8 years ago, and we want to talk about this stuff again. But as I'll indicate in a second, information doesn't get old, apparently. So let's move along. So this is what I was referring to, and this is a quote from the Gold Measures in Nova Scotia and Deep Mining that was written by Faribault back in 1999, and I'll just read this out here, and you can read along with me if you want. And it says, in certain thicknesses of sheets of paper or cloth bent into an anticlinal fold, a slipping of the several layers on each other will take place. The sides of the fold will be tightly compressed, while on the top, openings will be formed, saddle reefs. In the same manner, in the folding of this great thickness of strata, referring to the Goldenville group, the beds separated along the planes of stratification and moved along these planes, the upper bed sliding upwards on the lower inclined bed. This slipping is clearly proved by the striations and slicken slides that are to be seen in most mines on opposite bedding planes, and by a certain thickness of crushed black slates or gouged between the walls. Such movements naturally took place between strata where the cohesion was slightest, and thus we find quartz veins following layers of slate, especially when the slate is interbedded between thick beds of hard quartzite. So effectively, what I'm going to be talking about in this talk is that process and vein development. So we'll go back over 100 years ago, and in some sense, they had already figured it out. And, sort of like reinventing the wheel, if you want. So just a quick outline of what I'm going to be talking about. First, I'll give a review of the regional structural setting. Then we'll look at, I'm going to spend a few minutes on the regional stratigraphic setting, or not, of these gold deposits. Then we'll look at the local setting of them and what information we can get from that, and then look at the structure of the vein arrays, and finally, I just want to spend a few minutes on grade control, or controls on grade, not grade controls. So I forget. I got a few. I'm a little older than I used to be, and I've found myself just writing a few notes down so that I would remember relevant things to say as we're going along here. So. Okay, just a map of Nova Scotia, just for those people who may not be completely familiar with it, or those that are from away. We have a couple of people from away here. The Meguma terrain is a pretty simple terrain. It's dominated by, can I ask if I have a pointer? It's in the remote. The bottom button? Okay, good, thanks. Ooh. Back here again. So the Meguma group is this mustard-colored group here, which is the Goldenville group, and the slates in the sort of the gray color here. And those are the rocks to the Meguma terrain. And as we can see by the trend of these things, they give us an indication of the structural grain related to folding. That was foldings related to the Acadian deformation, and these pink units on here, of course, are granites, which are largely post-tectonic, and then sitting on top of those are some green rocks and some blue rocks here, which are carboniferous and younger, and not relevant to this talk, although they have important deposits of gypsum, coal, salt, and other industrial minerals. All the red dots on here, of course, represent gold deposits, and so we can see there's lots of gold deposits within the Meguma group. And one of the things that we can get, one of the bits of information we can get from the distribution of these things and the number of these things is the fact that there are lots of them, and there's similarity to all of these deposits, as we know. So there was some sort of a terrain-wide, event, if you want, that was producing these gold deposits. This is an old map from 1912 that was produced by Fletcher and Faribault, And from the eastern shore there, you can see the inset there. And so this is the eastern shore area. And it shows the distribution of gold deposits within the eastern shore by these white dots, if you want. And certainly by this time, it was recognized that these gold deposits occur in the hinges of regional folds. And that's what's shown as the white lines here as anticlines and synclines. What they did as well with on this particular diagram is that they show the distribution of the veins with respect to, they refer to them as domes, because where these things occur, a lot of the gold deposits occur in domes within the anticlines. And what they did was they shaded the area of this ellipse here, if you want, where the veins occurred. And what you can see is that in some cases they're at one end of the fold or other, and in some cases they're on one limb and or another limb. And in a few slides from now, we'll have a look at some cross sections through here that'll sort of show why these things are shaded like they are. And hopefully by the end of the talk, you'll understand why they're where they are. So this is a cross-section through, a couple of cross-sections through the Meguma group on the eastern shore. I don't have a map showing it, but it's not really relevant. A lot of people will recognize the names of all these deposits. And the important thing here is that it shows the locations of these deposits within the hinges of regional anticlines. So again, just by looking at simple cross sections like this, it gives us some information about the origin of these deposits, which is where I'm trying to go with this talk, is how these deposits were formed and what controls their distribution, et cetera. So the fact that these things are all in the hinges of regional folds is clearly important in telling us something. And that may seem obvious for most of us, but as we know, there's been lots of different hypotheses on how these gold deposits formed, and I'll look at one of those a little bit later in the talk, and hopefully convince you that the evidence points towards the model that I'm proposing, which is this late flexural slip saddle reef deposit model, if you want. So just looking at, that was sort of things on a regional scale, and we can see that the deposits, if you want, at that level are certainly focused within the hinges of regional anticlines. Obviously a reason for that. If we look at things at sort of at a deposit level, smaller cross sections here, a couple of different deposits, what we can see is that the veins, which are shown in yellow here, have a very systematic distribution. If you have a chevron type fold like this, then you'll have veins on both limbs. If you don't, if you have a sort of monoclinal structure like this, where you've got a steep limb, and or folds like this, where there's somewhat asymmetric, where you have a steeper limb and a shallower limb, what we see is that the veins are always concentrated on the steepest limb, if you want. So again, this is telling us something, constraining things with respect to how these deposits, or how these veins at least, developed. Okay, I said I was just going to talk briefly about stratigraphic control of these deposits. There's been suggestions in the past by a number of different people, not, you know, been 3 or 4 people that have suggested there's some stratigraphic control on the distributions of gold deposits. This one's from paper by Ryan and Smith in 1998, where they suggested that there was not suggested, but they correlated the deposits with stratigraphy that was defined within the Meguma group within the Halifax area. And so they've got two columns on here. One is the top 20 producers, and the other one is for all the producers. And you know, suggesting that there's a correlation between the distribution of the gold deposits and certain stratigraphy. And a couple of things I want to point out there is, number one is the stratigraphic position has not been established for most of these deposits because it's not been established on the eastern shore where most of the deposits occur. So fitting these things to stratigraphy that's not been defined, you know, doesn't seem to be that strong of an argument. And the other thing with respect to the 20 producers, 20 largest producers, that's based on their historical production, and I would argue that, you know, we all recognize the fact that most of these deposits were not, you know, mined to exhaustion, and therefore we don't really know the size of them, and some of the smaller ones might actually be the larger deposits. So that doesn't mean that there's not potentially some stratigraphy to be recognized on the eastern shore. And I put this. This is from this is from Sharon Lee's MSc thesis in 2005. And there's the Muscatava batholith in the River Lake Pluton up here for reference. And what she did in there was she recognized that you could see distinct magnetic patterns, you know, throughout the, and we have good aeromagnetic data on the eastern shore, and that you could, you know, define these units, if you want, magnetostratigraphy throughout the eastern shore. And in the cross section down here, she does the same thing. The profile of the magnetics on the top there, and then the units that in green and brown there that she's reflecting, saying are being repeated through here. So. You certainly can use this concept to look at the distribution of gold deposits with respect to stratigraphy. And anybody that's going to look at that sort of thing, I would recommend that they try to source out a copy of that thesis, which you can find in the library at DNR. And I did a similar thing in 2007. It was the last thing I did with the department, actually, was to do some mapping in the eastern shore. And again, on this magnetic map here, that's the Muscatava batholith down there. This light's fading out, sorry. And then based on geological traverses down through the center part of the province, came up with this stratigraphy, and that stratigraphy, it's not so obvious here, but it matches up with the magnetics quite well. And the idea was to try to see if I could recognize the stratigraphy that was apparent in the magnetics. And it was challenged, but it is there. And this is a cross-section down at the bottom here through that area, and what I want to point out is that, you know, just pop the different deposits that occur within that area, and you've got, you know, the Caribou near the contact with the Halifax. You've got the Moose River deposit deep within the stratigraphy at the lowest stratigraphic level, and you've got other deposits halfway up. So all deposits, you know, occur in the anticlinal hinges. They occur throughout the stratigraphy, and so I say structure trumps stratigraphy, and no real convincing, compelling argument that stratigraphy is important. This is another diagram that's been thrown around for some time, and just looking at the Halifax group in green up here, and the Goldenville at the bottom, and looking at the distribution of gold deposits. And as you can see, you can find gold deposits all the way through the section. And in fact, one of the things that most of you have probably seen at one time or another is this diagram. Again, this is from that Faribault paper in 1899, and where he promoted the idea that these deposits probably had a lot of depth extension to them, and that they were essentially focused in the hinges of anticlines. And with that concept, if you think about these deposits that we're looking at on this other cross-section in blue here, and you look at the potential for that to occur, what you'll find is that you're migrating up and down through a lot of stratigraphy, and again, that points to the fact that if you accept this possibility, then it would suggest that stratigraphy plays little role in the distribution of these deposits. So looking at these regional folds in a little bit more detail, and we recognize the fact that obviously these anticlines are important for the localization of these deposits. Folding was, the folding mechanism that produced these folds is likely important in terms of development of these deposits. So what do we know about them? Well, they're box folds or chevron type structures with straight limbs. We can see that from the cross section. That type of fold they're referred to as parallel folds, and the folding mechanism is flexural folding. And one of the other things we know about this is that there's hinge migration. And at the bottom here, there's just a sort of schematic diagram as to how these types of folds initiate, and then how they mature into eventually into just a series of chevron folds. So we know that there's hinge migration related to the fold development, and that's an important thing in terms of understanding why these deposits when these deposits developed. Hopefully, I'll come back to that. So in terms of flexural folding, just a little bit of background on it, if you want. That quote from Faribault sort of summed it up early on. It's like I use the analogy of a telephone book and folding it, and pages slip over each other as you do that, and you get a certain amount of shear strain. An important concept, which I will come back to, is the fact that the amount of shear strain that you have at any particular time is a function of the limb dip, and as you can see here, it's not linear. It's exponential if you want. You get with steep limbs, you get a lot more shear strain than you do at low limb dips, and that's an important point that, as I say, I'll come back to again. So let's just go through the vein array if you want. There's lots of different ways to classify veins, and people have done it over including in the Meguma. Sometimes you'll use textures or mineralogy. There's crack seal veins or laminated veins, massive veins, saddle reef veins, all kinds of different plagioclase bearing veins. The classification that I like to use, I simplify because I'm generally a simple guy, I guess, is just how the veins are related to the fold. And so, and this is from my experience looking at several of these deposits, most of which we'll see examples of as we go through this. And so I've classified them as bedding concordant veins, which include saddle reefs, laminated veins, on echelon veins, or just massive type veins, cross veins, and angulars. And angulars I'll come back to later in the talk, but the other ones I'll go through examples of these different veins now. So with saddle reefs, saddle reef development is extremely well known from work that was done by Ramsey back in 1974. There's no mystery about them. They form latent fold history, and where you get dilation in the hinge zone, just as was being described by Faribault in 1899. So we know that they produced late in the fold history. Just some examples of them. This is from the ovens. Dan and the crowd were down there yesterday, probably getting their own photographs of people sitting on this, but just a small saddle reef that's exposed down there. And this is a better, well-known example from the Dufferin mine on the second saddle. And one of the things about saddle reefs is that sometimes people seem to think that they're not that common. And of course, Dufferin is the type example, if you want, of saddle reefs in the Meguma. And some previous workers have suggested that they're not very common. But in fact, if you start looking through reports, and in particular Faribault's maps, and if you look at them in detail, he'll have reference to saddles. They may not be abundant, but he has reference to saddles in most of the deposits. And here's just a list of deposits where I've either seen them or seen them in photographs. So they are quite common. Okay, on echelon bedding concordant veins. This is a vein type that I wasn't really familiar with until I started doing some work underground at Dufferin and at Mooseland, where I found these things, and I thought, well, these aren't very well documented, but you start talking to people, and apparently they've been noted at many deposits in the 80s and such, and you start looking through photographs of people's collections and stuff, and you start finding more of them. So I think that they're quite a common vein type within these Meguma deposits. You can sort of see the location of these things if you want, with respect to the fold. They're just the limb of, and in this particular case, it's at Dufferin again, and we're looking at saddles that are up above these on echelon vein sets, and just over here there's a laminated bedding parallel vein as well. So. And the nice thing about these veins is that, like saddle reefs, we know lots about them. And there's a close-up photograph down here where we can see the character of these things. They have these little pegs on the ends of them, if you want, and that's bedding like this, and you can see cleavage, and what I've referred to as L1 there is the bedding cleavage intersection lineation, or the hinge of the fold, and those pegs are parallel to that. So they clearly relate it to the fold. And here's just a diagram that quickly explains the development of these things. If this was in a shear zone somewhere, nobody would have any trouble understanding how these things develop. They're just referred to as on echelon shear veins, if you want. They initiate like this, and they'd be, in this particular case, relatively horizontal. And then as the fold develops and you get shear on the limbs, they rotate around, and eventually they look like this. And that's what we've got in the photograph here. So it's, understanding these things is not particularly difficult. But it tells us something about the environment of development of these veins. Okay, laminated bedding parallel veins. These things are the ones that people tend to focus on. There's those ribbon veins or laminated veins that we commonly associate with gold mineralization in the Meguma. They're quite common. A lot of times they are planar, like this one. This is at the Dufferin deposit, and this particular laminated vein is a down dip extension of a saddle vein. And so there's a relationship with it, and I'll come back to the relationships of veins shortly, but the important thing is that, in this particular case, it's planar. Sometimes they're buckled. They occur, we can document the fact that they occur in flexural slip movement horizons, and they have striations on them that represent that. And as I say, they're legs to saddles sometimes, and sometimes they have a composite texture. In other words, there's laminate portions of the veins and then later massive veins. That's probably part of the saddle event. So this is just a photograph here showing that these things occur along flexural slip movement horizons, and that movement horizon is defined by this offset discordant vein here. One of the things that a lot of people historically looking at these things would have said was that these discordant veins are much later than the laminated veins, but it's pretty clear here that the opposite is the case in this example. As I say, sometimes they're buckled. This is a beautiful example of a really tightly folded vein in the hinge of the Dufferin anticline. This was the old Dufferin mine, and again, I would note the fact that you're getting these types of tightly buckled veins in the hinge of an anticline associated with saddle reef deposits, which typically wouldn't be considered to be associated, but we're seeing them spatially associated here. There's just striations on a nice vein from the Tangier deposit where there's good examples of this, and those striations are down dip and consistent with that flexural slip mechanism, if you want, or as Faribault said, just the dragging of one bed over the other. And so I'm just going to go on a quick distraction and look at this pre-folding hypothesis that has been put forward in the past and say a few things about that. What was suggested was that you had pre-tectonic hydraulic fracturing parallel to bedding here, different mechanisms to come up with that. You can choose your own. And then you had layer parallel shortening. That was before you had any regional folding, though. And so at that time, you buckled these folds. And then finally, you had regional folding, and you result in these parasitic folds that were this type of thing. And the key thing about that is that if that's the case, these things should occur on the limbs of the folds, in the synclines, and et cetera. And to no surprise, there's been lots of argument about whether you actually find that minor folding on the limbs or not. But this photograph here I particularly like because I think it demonstrates quite clearly my point, which would be that you can see lots of folding of layers and of quartz veins in the hinge of this is at the ovens anticline, but on the limbs of the fold, there is no minor folding. And I'll show you a few more examples of that in a second. So, the argument, or my opinion would be that what's happening is that because in this particular case, you've almost got like a little box fold up there, and because that's in a favorable position to be shortened late in the folding history, that folding is late. You didn't have it form early, and we know that one of the most compelling reasons for that is because they're not on the limbs, and everybody recognizes that flexural folding was a dominant fold mechanism, and you can't get rid of parasitic folds through flexural folding, and therefore they were never there. And just a couple more examples, and again, these are from the ovens. You can see some in here. You can see some tightly folded veins, and down here right in the hinge area and in on those same veins as you go down to the limbs of the fold. And we're looking at a down plunge of this fold, so kind of like an oblique cross section. And so we can clearly see that the folding is only limited to the hinge of the fold. Okay, cross veins. Here's a photograph, again at the ovens. This is a bedding surface. We're looking at a conjugate set of cross veins that are very systematic. When we plot that data up on stereo nets, what we find is that the two sets are one in red and one in black. They're the poles to these veins cluster very systematically. And if we look at the intersection of these veins, they form a nice girdle like this. So very systematic, and they're essentially just profile. They form along the profile of the fold, if you want. One of the things that previous people looking at these deposits have suggested is that these discordant veins, as I mentioned earlier, that they're later, not related to the auriferous veins, in particular those laminated veins and buckled veins. And I just show this as an example. Hopefully you can see some nice nuggets of gold. And this is probably the richest vein that I've ever seen. It's not a big vein, and it's a discordant vein at the Ovens deposit. So that squashes the myth about AC veins. And I don't know, it's probably likely that Dan's going to talk about these types of textures, these laminated veins, but something of interest here, and I just throw up out of interest, nothing else, is that this is a discordant vein. As you can see, stratigraphy is this way, and typically we think of these laminated veins as only being produced as layer parallel veins, but obviously there's more to be understood about those. So next I want to talk about the flexural slip vein array and the fact that these veins are all related, and we see cross-cutting relationships between concordant and discordant veins. We see laminated veins that are the down limb extensions of saddle veins. Same thing with on-echelon veins. There's a spatial association with all these different veins, and you get high concentrations of all vein types when you're in a deposit. And in terms of understanding them, the kinematics of these things are all consistent with a fold-related origin, and they're mixed in with other structures related to flexural slip folding, such as just dry movement horizons. So the idea is to we'll look at some data here, or some photographs and examples of that demonstrate that you had synchronous emplacement of all these different vein types, and in that regard, it's a true vein array, if you want. Here's a couple of diagrams from this was from some examples down at the Ovens, and you can clearly see that with respect to the horizontal lines in this diagram here are bedding parallel laminated veins, and the other colors are just different generations of discordant veins. And we can see all kinds of mutual cross-cutting relationships with some veins that are cut by laminated veins. Sometimes they seem to be following each other, lots of examples of those, and sometimes they post-date the laminated veins. So, this all suggests to me that you had these mutual cross-cutting relationships indicate that you had synchronous emplacement of all these different vein types. There's a bunch of photographs from the Dufferin mine. In the middle here is just a little cross-section showing different saddles and arrows pointing to where these things come from. And as I was indicating before, you've got, this is a saddle vein up here, The down dip extension is a laminated vein. In some cases, the down dip extension is on echelon type veins. Sometimes you get laminated and on echelon type veins together. So the relationship of all these veins, supports the idea that they were all formed during the same event. And this is a photograph of the leg of one of those saddles, fairly large one here, about 1 meter across. And we could see that there's the major saddle would be up above this. And we can see, massive type of leg, if you want, that would migrate down into a laminated vein. These are on echelon veins right there. We've got cross veins going into the wall. This is a flat line vein right here. So there's a whole mess of veins, and it's clear that these things are all associated, all related. So just sort of a summary, I guess, of that. We see that all the veins have a geometric and kinematic relationship to folding, and therefore can be related to flexural folding. And synchronous vein development, and therefore it's reasonable to classify them as a vein array. And one of the important things that people have to come to terms with is that a general model, if you're going to have a general model for these deposits, you've got to explain all the vein types because they're all related. Nice to be picky, but we can't be. So I indicated earlier that shear strain was, I think, an important concept in why we get what we're getting in these deposits, and why we get these concentrations of veins where we get them. And I'm just going to very quickly go through a bit on that. So the important things for shear strain is always trying to find things that record it. And if it wasn't for veins, we wouldn't have anything. And we've got two different things that we can use here. We've got displaced quartz veins, and we've got on echelon quartz veins that both give us a sense of how much shear strain there was and when it occurred. Because we know that displacement is, or that shear strain that we're looking at, whether it's displaced veins or on echelon type veins, we know that that's the last thing that occurred in terms of that flexural shear, because if there was any more, they would have been deformed more. So this is just, this is a lot more complicated looking than it is, and I'm just going to summarize this down very quickly in the fact that there was, fortunately, a couple of nice sections on the, am I ever going to get this right? There was a couple of sections at the ovens where I could actually measure the displacement of these veins over continuous sections. And when you look at that and look at the amount of shear strain and assume that it's the last bit of shear strain instead of the first bit, what it indicates to us is that at a final limb dip, which at the ovens is 70 degrees in the particular one I was looking at, you can accommodate a significant amount of shear strain recorded by these displaced veins by a very small change in limb dip. 3.5 degrees will give you like a half a gamma of shear strain, which is significant, and I think an important concept in this. If we look at on echelon veins, we know, again, as I indicated earlier, we know lots about the formation of these things, and they start out like this. It might be hard to see, but flat like that, and they get rotated around. And we can measure the amount of shear strain associated with that based on the orientation of the pegs, which we can see on the ends of these things, which represent the original orientation, and where they are now. And these ones have clearly been rotated a lot to the point where they're in an extensional field and they're getting boudinaged. And there we can see a significant amount of shear. Now, very, very quickly, if we use that concept to understand the amount of shear strain, and we assume that there's 10% of the sequence is slate and all the shearing is being focused into the slates, then this is what happens to on echelon shear veins that, sorry, that start out at, if we start out at a limb dip of 60 degrees, go to 65 and then to 70, that's what happens to those veins. And you know, these veins are the types of things that we're seeing in these deposits tend to look like these last two. But the important thing is that you don't have to have a lot of change in limb dip to get that amount of shear strain, to get that geometry of veins. So just quickly on just to sort of finish on this shear strain thing, you know, the flexural strain is partitioned in the steep into the slate layers. At high limb dips, you get an extreme amount of strain, and that significant flexural shear associated with a late fold tightening, if you want, can result in a lot of structure development and veins related to those things. So if we look at this, if we were to look at this diagram over here and say, well, all those veins, if we were to back this off maybe 10 degrees earlier in fold development, maybe there were no veins there at all. Just, I want to go spend a few minutes, because I only have a few minutes left, I see here, on grade control, or control of grade. And these are just a couple of small clips out of Faribault maps. And the important thing, you may not be able to even read them on there, is he's identified things like angulars and pay shoots. The dip of pay streaks over here, and the dip of pay shoots on this diagram over here. So this is a concept that was recognized by the early operators and documented by Faribault, and we look on most of his maps, and we're going to see reference to things like that indicate there was some focusing, if you want, of good grade within these deposits. And I'd suggest that maybe that's been a lost art, because, you know, with mechanized mining now, we tend to think we can just go in and mine everything. And I think the important thing is that we want to mine ore, not veins. So this concept of angulars, I'm just going to briefly go through, because I saw some good examples of these in a couple of deposits I was fortunate enough to work at. And anybody working in the Meguma for any extended period of time, I'm sure has heard the term angular. And there was some reference by Faribault and then another guy, Armstrong, 1937, and that paper is in the DNR library, and I would recommend people get that if they're trying to understand this concept. They just sort of describe them as discordant veins which intersect bedding at an angle and locally follow bedding concordant veins, and they've been considered to be important for mineralization in many of the deposits. And where these things intersect and overlap is what defines ore shoots, and they have certainly been considered to be important in the past for defining what's ore and what's not. And this is just a very general representation of what angulars are, how they're described, because I haven't seen a lot of documentation of them, but you've got strike parallel, but bedding discordant veins that locally become merged and overlap with these bedding parallel veins, and it's in that zone there where the enrichment has been described. And I'm just going to look at two examples. The first one is at where I've seen them at Mooseland, and this diagram is just to show you, give you a setting for the deposit. There's some nice saddle veins, and we saw those on field trip a couple of days ago. That go down into these legs, which is what they were mining, defined by laminated veins. And there was one there in particular called the Little North Belt, which is down here. This was a cross section that I did, and we'll focus in a little bit closer on that. So here's the Little North Belt here, the decline coming down there. That's a drift going in on the Little North Belt. The red lines there represent the bedding parallel veins, and the yellow lines here represent angular veins. And an important thing about them we can see is that they're strongly folded. This is the envelope of one of those veins down there. And you can see that the orientation of that, the fold hinges on that angular vein are quite steep. They're around 45 degrees plunging to the east. And we can see the intersection of those veins with bedding surfaces in there. This is shows a couple photographs, same diagram down here, a couple photographs. We're looking at the profile of there was 3 particular veins in there. And up here we're looking at a back view if you want. So we're looking at the ceiling of the drift. And here's one of these angular veins right here coming in. And you can see where it comes in here. It turns and follows along the bedding parallel vein and thickens it. And it's in that interval there where you could visually see abundant coarse gold, commonly at the margins of that white massive quartz and the laminated vein. And so there was clearly a control on where at least the coarse gold was. The sampling that they did along this drift related to that. They had good grades in the areas where these angulars overlapped, not so good grades where they didn't overlap. So don't fully understand these things, but empirically you can see them, they're real, and probably an important feature, these things and other potentially other secondary structures that control the grade of ore in these deposits. How they form, these angular veins, this is just a suggestion down here in the bottom that they may be analogous to on echelon type veins as they form at an angle to bedding, and then as folding develops, the vein itself gets strongly folded. The only note that I would make here, and it's something I've never reconciled, is the fact that the hinges to these folds are not parallel to the hinge of the regional fold, and therefore it's difficult to associate that folding with the regional folding. And these green arrows would represent the direction that you probably shouldn't be mining, not this way. This is another example from the Forest Hill deposit, and we can see the workings underground. These workings were from the Seabright and West Miner days down here. Some of the earlier stopes up here from earlier workings, and what we can see here is that there's an orientation to these workings, and they plunge down to the east. In this particular case, that plunge is approximate to the regional fold hinge in that area. So you could relate to potential ore chutes related to angulars, and they had angulars there. They're not well documented. You talk to the people that worked there, and they had what they referred to as these 7 structures, and that was the geometry of what they looked like. But when they described them, they were clearly angulars that came in from the wall rock, followed along and went out again. By the time that they were well along with the mining here, they understood them, and they were able to actually mine these things and successfully. But you can see when my understanding is, I wasn't there at the time, but my understanding was that when they first started out, they had tracked vehicles, and they were mining these things horizontally as a result of their decision to use tracked vehicles for moving ore. And there was I was talking to Ken Adams, that was the mine geologist there, and it sounds like the standard geological engineering conflict, as happens in a lot of mines. The engineers would tell them that you're not giving me the grade that you told me you were going to give me, and he said, well, you're not going where I told you to go, and that's exactly what, once they reconciled that and they realized that there was a plunge to these things and they started mining them appropriately. Again, my understanding is that for the last several months of the mine there, they were mining at 12 grams to the ton. So the importance of of understanding these things, I think, can't be. Okay, and just a summary, just to finish up here, just a brief statement. You know, hopefully I got across the point that you know, folding and in particular the flexural slip folding mechanism late in the fold history, when lots of strain occurs on steep limbs, gave rise to these Meguma lode gold deposits. Thank you.